You were probably taught in school that the circumference of the Earth is one simple number, 24,901 miles. But what if I told you that's a lie? Okay, maybe not a total lie. But it's only half the story. The truth is, there are two Earth circumferences. And the difference between them is about 41 miles. That lie is the key to understanding why our planet has a waistline, and how a librarian 2,200 years ago used nothing but a stick and his brain to first crack the code of our planet's true size. The planet's waistline. So, where does this 41-mile difference come from? It's because of a simple fact that complicates everything. The Earth isn't a perfect sphere. If you saw it from space, you wouldn't see a perfect marble. You'd see something more like a slightly squashed orange, a shape that scientists call an oblate spheroid. It's wider around the middle than it is from top to bottom. This shape is a direct result of the planet's daily spin. As the Earth rotates on its axis, it generates something called centrifugal force. You've felt this yourself. It's that outward push you feel when a car takes a sharp turn, or the force that sends water flying off a spinning bike tire. Now, imagine that force acting on a planetary scale for billions of years. Earth's constant rotation has caused it to bulge outwards all the way around the equator. It's a permanent feature, a planetary waistline. This is why we have two different numbers for the circumference. The one you probably know, 24,901 miles, is the equatorial circumference, the distance around that bulge. But if you measure the Earth from the North Pole to the South Pole and back again, what's called the polar circumference, the distance is shorter, about 24,860 miles. The difference between those two paths is roughly 41 miles. It's not a huge number in the grand scheme of things, but it's a massive clue about the forces that have shaped our world. But long before we could ever dream of measuring this bulge with satellites, one of the greatest minds of the ancient world figured out that first number with stunning, almost unbelievable, simplicity. The librarian who measured the world to find out how we first got a handle on our planet's colossal size. We need to travel back in time. Not to the age of rockets, but to ancient Greece. Around 240 BC our story starts in the city of Alexandria, a bustling hub of knowledge in Egypt that was home to the most famous library in the ancient world. The head librarian was a man of incredible genius named Eratosthenes. He was a true polymath, a geographer, mathematician, astronomer, and poet. His friends even nicknamed him Pentathlon, after the 5-event Olympic athletes, because he was brilliant at so many different things. Eratosthenes, like many scholars of his day, already knew the Earth was round. They'd seen the Earth's curved shadow on the moon during a lunar eclipse and noticed how ships seemed to sink below the horizon as they sailed away. But the big question was, just how big is this sphere? The key to solving this puzzle came from a curious report from a city far to the south called Syene, near modern-day Aswan. Eratosthenes heard that on one day a year, the summer solstice, at high noon, the sun's rays shone directly down a deep well, lighting it all the way to the bottom. That meant the sun was perfectly, vertically overhead. No shadows. This sparked an idea. Eratosthenes knew that back in his home city of Alexandria, this didn't happen. On the exact same day, at the exact same time, a vertical stick in Alexandria did cast a shadow. He realized the difference in shadow angle could only be because of the Earth's curve. Here's where his genius really takes off. He assumed, correctly, that the sun is so far away that its rays hit the Earth as parallel lines. So the only reason a shadow appeared in Alexandria while there was none in Syene was that the two cities were on a curved surface. The angle of that shadow, he figured, must match the angle of the slice of Earth between the two cities. So, he did the experiment. He measured the shadow cast by a vertical pole in Alexandria on the solstice and found the sun's rays were about 7.2 degrees off from being directly overhead. A full circle is 360 degrees. 7.2 degrees is almost exactly 1/50th of a full circle. Eratosthenes reasoned that if the angle between the two cities was 1/50th of a circle, then the distance between them must be 1/50th of the Earth's total circumference. He had an estimate for the distance between Alexandria and Syene, 5,000 stadia, a measurement probably taken by trained walkers who literally paced out long distances. All he had to do was multiply that by 50. His result was 250,000 stadia. Now, historians debate the exact accuracy because the stadion wasn't a standardized unit. But depending on which version he used, his estimate was somewhere between 2% and 16% of the real value. An absolutely staggering achievement for a man with a stick, his intellect, and a lot of curiosity. He gave humanity its first real sense of the scale of our world. The twist, a second circumference for more than 1,000 years, the idea of a single circumference, the one Eratosthenes had so brilliantly estimated, was the standard. But the story wasn't over. In the 17th century, a new giant of science came along who would add a crucial twist: Sir Isaac Newton. Newton wasn't just thinking about Earth's size, he was figuring out the fundamental forces of the universe. His theory of gravity explained why we're stuck to the ground, but his laws of motion also gave him a wild insight into the Earth's shape. He thought about that same centrifugal force. Newton realized that on a spinning planet, this outward force would be strongest at the equator. He reasoned that when the Earth was forming and more of a fluid, this constant push would have caused it to bulge out. Basically, Newton predicted the Earth's equatorial bulge using just math and physics. He argued the Earth couldn't be a perfect sphere. It had to be an oblate spheroid. This was a radical idea. It meant Eratosthenes' measurement along a north-south line was just one of two circumferences. There had to be another, longer one around the bulging equator. This kicked off a huge scientific debate. To settle it, the French Academy of Sciences funded two daring expeditions in the 1730s. One team went to Lapland, near the Arctic Circle, and the other to modern-day Ecuador, right on the equator. Their mission: measure the precise length of 1 degree of latitude in both places. If a degree was longer near the pole, Newton was right. After years of brutal work and extreme weather, the results were in. The Lapland expedition proved it. A degree of latitude was in fact longer closer to the poles. Newton was right. The lie of a single circumference was officially busted, replaced by a more complex and fascinating truth: our planet has two. If you're enjoying this deep dive into scientific history, do us a favor and hit that like button. And if you want to keep uncovering the secrets hidden in our world, make sure you subscribe, because we have even more to explore. Why the 41-mile lie matters today: so we have a polar circumference of about 24,860 miles and an equatorial one of 24,901 miles. A difference of 41 miles. Why does this seemingly tiny detail matter today? Well, it matters a lot, because almost every technology that needs to know where you are depends on it. Take the GPS in your phone. To pinpoint your location with an accuracy of just a few feet, the system can't treat the Earth like a perfect sphere. The satellites and your phone must use a sophisticated model of Earth that accounts for its real, squashed shape. Without that correction, GPS locations would drift by miles. A flight from New York to Tokyo would be calculated on a wrong path. Surveying land, mapping coastlines, and even drawing international borders all rely on knowing the Earth's true shape. For them, that 41-mile difference isn't trivia, it's a critical number in the equation. But the story gets even more complex. Today, scientists know that even oblate spheroid is a simplification. The Earth isn't smooth, it's lumpy. It has huge mountain ranges and deep ocean trenches. The density of rock under us even changes from place to place, causing tiny variations in gravity. The true, lumpy shape of the Earth, if you average out the tides, is called the geoid. Modern science is constantly using satellites and gravity measurements to refine our model of this geoid. In a way, we're still continuing the work Eratosthenes started, just with tools he could have never imagined. That lie of a single circumference wasn't a lie after all. It was a beautiful simplification, the first step on a long journey of discovery that takes us from a perfect sphere, to a squashed spheroid, and finally to the complex, lumpy reality of the geoid. So, the next time someone brings up the size of the Earth, you can tell them the full story. It's not one number, but two. It's about 24,901 miles around its bulging equatorial waistline, and about 24,860 miles on the shorter path around the poles. That 41-mile difference is more than just a number. It's the signature of our planet's daily spin, a mark left by billions of years of turning in space. It's a testament to human curiosity, from the simple genius of Eratosthenes and his shadow to the satellites that map our world today. It just goes to show you that the world is rarely as simple as it looks in a textbook. The truth is usually more nuanced, more complex, and way more interesting. What do you think is more mind-blowing? That the Earth has a 41-mile waistline, or that someone figured out its size over 2,000 years ago with a stick? Let me know your thoughts in the comments. And if you enjoyed unraveling this bit of science history, be sure to like and subscribe for more stories that challenge what you thought you knew. Thanks for watching.